A geometric sequence is a particular type of sequence that's created by multiplying each value by the same term, and we call that multiplied value our common ratio. And we use R to represent that in our equation. And again, we'll get to that later. So if we're looking at this example, the way we find our common ratio, an easy way, is just taking the second term divided by the first term. So if we do 12 divided by 3, we get 4. And if we test it out here, we can see that 3 times 4 gets us 12. 12 times 4 gets us 48. And 48 times 4 is 192. So this would be a geometric sequence where our ratio is 4. Okay, so let's look at a couple of others. So again, we can find our common ratio by taking the second term and dividing it by the first term. So 32 divided by 64 reduces to 1/2. And to test it out to make sure it is geometric, half of 64 is 32, half of 32 is 16, half of 16 is 8, and half of 8 is 4. So the common ratio would be 1/2 in this case. All right, and let's do the last one. So again, second term divided by the first term, which we would do that by multiplying by the reciprocal. So here we get -2/3. And again, let's test it out to make sure it works. If I do -2/5 times -2/3, that gets me 4/15, which I got. And if we multiply that by -2/3, I get -8/45. So my common ratio is -2/3. So because this is a recognizable pattern, there is a general formula for geometric sequences. It's very similar to arithmetic sequences, but instead of a difference, we have a ratio. So the formula is U sub n equals our first term times the common ratio to the power of n minus 1. And again, I don't like to just give you the formula, so let's actually break this down and see why that works and how that happens. So over here, we've got that U1, U2, U3 listed out in a table with the values that we were given. And let's see what's happening here. So if to find our common ratio, we're going to take our 32 divided by 64, which gave us 1/2. It was the same one we did earlier. So if we're putting this in a table, 64 is our starting point. To get 32, we did 64 times 1/2. To get 16, we took the previous term, which was 64 times 1/2, times another 1/2. And then to get our fourth term, we multiplied yet another 1/2. So to rewrite this, another way to write all of these things, this would technically be 64 times 1/2 to the 0 power, because anything to the 0 power is 1, so 64 times 1 is itself. This would be 64 times 1/2 to the first, 64 times 1/2 to the second, 64 times 1/2 to the third. So again, if you looked at the arithmetic sequences, it worked the same way. I'm taking whatever my term is, and the power, the exponent, becomes 1 less than that. So for 2, my exponent was 1. For the third term, my exponent was 2. So for my nth term, I would have 64 times 1/2 to the 1 less than n, so n minus 1. And if we go back to this equation and use the equation, it will look exactly the same. So un should be the first term, which is 64, times the common ratio, which is 1/2, to the n minus 1, which is exactly what we got in our table. So let's go through a couple examples. I would encourage you to pause the video and try the examples on your own and then play and see how you did. All right, so for this first one, we have a geometric sequence and we want to find the value of r and the value of u sub n. So first of all, to find the value of r, we can just take our second term divided by our first term like we did previously. So r would be 93/930, and that reduces to 1/10. So once we have r and we're given our first term, it should be pretty simple to put this into an equation. So as a reminder, our equation is u sub n equals u1 times r to the n minus 1. We have both of those pieces of information, so we're just plugging straight in. So u1 is 930, r is 1 over 10 to the n minus 1. So from here, if we want to find a specific term, so in this case we want to find u sub 9, we're just plugging in 9 for n. So u sub 9 would equal 930 times 1 over 10 to the 9 minus 1, which is the same thing as 1 over 10 to the 8th. So we've got 930 times 1 over 4, 5, 6, 7, 8. And then we just evaluate that in our calculator, and that comes out to 0.1234593. And that's it. So your ninth term would be that value. Okay, so moving on to number 2. So this time we're looking at a geometric sequence, and we're given the first term and the fourth term. And we also know the value of the last term, so u sub n, my last one, would be 196,608. Okay, so as always, I want to try to make an equation with this. I have my first term, but I don't have my value of r, and it's a little more tricky to get my value of r in this case. So let's write out what we know. I know my first term, u1, is 3. I don't know my second, I don't know my third, but I know my fourth term is 192. So we want to think about what we know about geometric sequences. For r, I know if I take u1 and I multiply by r, that's how I get my second term. And then if I do that again, that's how I get my third term. And if I do that yet again, that's how I get my fourth term, which is 192. So I have enough information here to solve for r. I know if I take 3 and I multiply by r times r again, it will give me 192. So I'm going to write this out. So 3r cubed would be 192. And then we can solve this equation for r. So if I divide by 3, I get r cubed equals 64. And then take the cube root, so r would be 4. So now I have r and I have u1, which means I can make my equation. So we're going to go ahead and do that. So u sub n would be 3 times 4 to the n minus 1. And now I can use this information that I gathered before to figure out what n would be equal to, which would be my last term. So u sub n is 196,608, 34 to the n minus 1. And now I need to solve this equation for n. So first thing we're going to do is divide both sides by 3, and we get 65,536 equals 4 to the n minus 1. So once you get to this point, I'm solving for an exponent. So some of you may have learned logs already, and you could take the log of both sides, which would be a great strategy. If you haven't learned that yet, then it's kind of guess and check. So I want to rewrite this number right here as 4 to some power. So I'm plugging in my calculator, 4 to the 7th, 4 to the 8th. And it comes out that 4 to the 8th power is 65,536. So I'm going to rewrite that. And then that's equal to 4 to the n minus 1, which means that 8 would have to be equal to n minus 1. So n would be equal to 9. So in this sequence, there are 9 terms if 196,608 is the last term. Okay. So in this last problem, we're going to look at an application problem of geometric sequences. So we have the value of a car is depreciating or going down at a rate of 19% per year. We want to buy a new car today for $24,620, and we want to see how much it will be worth after 4 years. So let's think about what's happening. In just 1 year, you start off with a value of a car at $24,620, and then it's depreciating, so it's going down 19%. So 19% or 0.19 of that initial amount. Okay. Based on what we've done with geometric sequences, this subtraction sign is not going to work. So I can rewrite this another way. If I take out a common factor of 24,620, I would be left with 1 minus 0.19. And then if I reduce that further, then I get 0.81. So what this means is I am retaining 81% of the value each year. So after the first year, it's only 81% of what was initially there. And in the second year, we would do that again and again. So this value, 0.81, is my value of R. So if we know that, then writing this equation should be pretty simple. We have the first term. We now know what R would be, so I'm going to plug that in. So U sub n would be my first term, 24620 times R to the n minus 1. And with my equation, I can go ahead and solve what it will be worth after 4 years by plugging in 4. So I've got U sub 4 equals 24,620 times 0.81 to the 4 minus 1 is to the third, and then I'm just plugging this into my calculator. So U sub 4 comes out to 13,084 and 8 cents when you round up. So what this means in context is if I start with a car that is $24,620, after 4 years, it's only going to be worth around $13,000. So just to recap, in this video, you should have learned the definition of a geometric sequence, the general form of a geometric sequence, which, as a reminder, looks like this, and some ways to apply geometric sequences to solve some problems. Thanks for watching.